All right, buckle up for a deep dive. We're tackling time travel paradoxes today. But don't worry, we're coming at it from a philosopher's point of view. The kind of stuff you guys really love to chew on. We're going to be digging into the Stanford Encyclopedia of Philosophy's entry on time travel and modern physics. And lucky for us, we've got our expert here to guide us through the mind-bending bits.
It's definitely a place where physics and philosophy get, well, a little messy. For ages, philosophers have been going back and forth about whether time travel is even logically possible. A lot of those arguments use paradoxes, like the good old grandfather paradox.
Yes, the classic. Go back in time, accidentally step on a bug that turns out to be your great-great-grandparent, and boom, you're erased from existence. Instant contradiction. But here's the thing that really gets me. What if modern physics, specifically Einstein's theory of general relativity, is hinting that time travel might be more than just a thought experiment?
That's the wild part. General relativity allows for some pretty strange structures in spacetime. Like, imagine a path through spacetime that loops back on itself. We call that a closed time-like curve, or CTC for short.
So like a cosmic highway that takes you back to your own past.
Yeah.
But wouldn't that just mean the universe is, like, overflowing with potential paradoxes?
Well, it's not so much that time travel has to create paradoxes, but it definitely forces us to look at our ideas about time and cause and effect in a whole new light. One way physicists try to make time travel fit with a consistent reality is this idea of fixed points.
Fixed points. Okay, I'm intrigued. Lay it on me.
Picture this. A photograph pops out of a time machine. You take a picture of that photo, get the film developed, and then that new film goes right back in time, becoming the original photo. Seems like a paradox, right?
Yeah, my head's already spinning. How can a photo be its own origin?
The fixed point idea says that even in a time loop, things can settle into stable states. Like, think of a coin spinning and eventually landing on heads or tails. In the photo example, the fixed point would be a photo with a completely even shade of gray. You could photograph it and send it back 1,000,000 times, and it'd stay the same. No more paradox.
So the universe kind of self-corrects to avoid breaking down, even when we throw time travel into the mix. Pretty neat solution. But does it work for every kind of time travel scenario?
That's a great question. And honestly, it's at the heart of some pretty heated debates. Fixed points might work in some cases, but they're not necessarily a one-size-fits-all solution. Not every system has these easily defined stable states. Some systems are like trying to fit a square peg in a round hole just doesn't work. And that's where we move from those straight-up paradoxes to this idea of underdetermination.
Underdetermination. Okay, now you got to explain that one.
So instead of saying time travel automatically creates impossible situations, we start thinking, well, maybe it just leads to a bunch of different outcomes that all make sense on their own. It's like one of those choose your own adventure books. Time travel branches out the story, but each path has its own logic.
So instead of the universe imploding when you mess with the past, it just gives you a range of possibilities that all work out. Less about can this even happen, and more about how could this happen without breaking reality.
Exactly. And to really dig into this, physicists use what they call toy models, these simplified ways to study how time travel might behave. One of the most famous ones uses something pretty unexpected: billiard balls.
Billiard balls. All right, now I'm really curious. How do those fit into all of this?
So imagine a billiard table, but instead of just a regular table, it's in this 2D spacetime with a CTC, a time loop. Physicists can then see how the balls would move and interact if they, run into this time loop. It helps us understand how even simple systems can get really complex and weird when you throw time travel in the mix.
So we're talking about billiard balls literally going back in time and, like, bumping into their past selves.
Kind of, yeah. And the crazy part is that sometimes the way to make everything consistent involves more billiard balls than you started with. Like, imagine a billiard ball gets sent back to stop itself from entering the time machine, a classic paradox setup. But instead of everything falling apart, another billiard ball, one we didn't see before, might pop out of the time loop to make a chain of events that makes sense.
Whoa. So the universe might just add stuff to keep everything consistent. Like it has this built-in paradox protection system.
You could see it that way. It really messes with our ideas of cause and effect. Time travel might not be about changing the past, but about the strange ways things can stay consistent. For a philosopher like you, this brings up all sorts of questions about free will and if things are already set. If the universe is always adjusting to keep things from breaking down, do we really have any choice in what we do?
Deep stuff. Definitely something to ponder. But let's change gears a bit. Moving past these theoretical models, what about actually building a time machine? Is that something that's even remotely possible, scientifically speaking?
Well, that's a big question, and there's a lot of debate around it. We got to be careful to separate the idea of time travel that might just happen naturally in the universe, like those CTCs, from us humans building a time machine in our garage. That second one is still, well, pretty far out there. It would probably mean messing with super strong gravitational fields or some other kind of physics we barely understand.
So, no, Back to the Future style time machines anytime soon, huh? But let's say, just for fun, that we could build one. Wouldn't that bring back all those worries about paradoxes?
Oh, absolutely. And that's where this idea of a partial Kachi surface comes in. Basically, it's like a snapshot of the universe before any time travel happens. The question is, can we tell from this snapshot if time travel is going to happen later on? Are there clues hidden in the present that hint at future time travel?
So it's like asking if the possibility of time travel is baked into the universe from the get-go. That really ties into those big philosophical debates about destiny, right? If we could see signs of future time travel in the present, wouldn't that mean things are kind of set in stone?
It's one way to look at it, yeah. It suggests that the universe might be set up in a way that allows for time travel or maybe even needs it while still keeping everything consistent. But it also makes you think, if time travel is possible, does it limit what can happen in the normal pre-time travel parts of the universe?
Like the universe is already taking future time travel into account and setting up boundaries so things don't get too messy.
Right. And these limits, if they're real, might not be like the regular laws of physics we're used to. They could be more like um, global rules that come from the way space-time is structured overall. It's complicated stuff that really pushes the limits of both physics and philosophy. It makes you question everything you thought you knew about cause and effect and what's really real.
Yeah. Definitely making my head spin. But let's switch focus again. Earlier you mentioned something called computational time travel and a paradox called easy knowledge. Can you break that down for us?
Sure. So physicist David Deutsch came up with this model where it's information, not physical things, that travels through time. Imagine a computer, but its circuits have a time loop built in. Some of the bits in the circuit get sent back in time, creating a CTC right there in the computer.
So it's like time travel for data. That's pretty wild.
It is. And it leads to this easy knowledge paradox. Say you give this time loop computer a super hard problem to solve, something that would take a normal computer forever to figure out. The time loop computer could solve it almost instantly because it has to be consistent. The loop forces it to have the right answer from the start.
That sounds almost too easy. Like time travel is the ultimate cheat code for solving the universe's hardest problems. What does that even mean for us, philosophically speaking?
Well, it's not quite that simple. This model makes some big assumptions, and it's tied to the many worlds interpretation of quantum mechanics, which is a whole other can of worms we could talk about some other time. But for a philosopher, it raises questions about what knowledge really is and how we figure things out. If we could use time travel like this, would it change how we see what's knowable and what's possible to compute?
It definitely seems like it would blur the lines between what we think is possible and impossible. But before we get too carried away with all these mind-blowing possibilities, can you give us a quick recap of the key takeaways? We've covered a lot of ground here.
We started off by, questioning that old idea that time travel paradoxes mean it can't exist. We talked about how modern physics, especially general relativity, suggests time travel might actually be physically possible, thanks to those crazy closed time-like curves.
Right, those CTCs, like time loops built right into space-time. And while they open up some amazing possibilities, they also make us think differently about those classic paradoxes, like the grandfather paradox.
Exactly. We got into the concept of fixed points, remember, as a way to make time travel work without contradictions. It's like, even with a time loop, some parts of reality just stay stable, and that prevents those paradoxical situations.
It's like the universe has a built-in system to keep itself from falling apart, even when things get wild with time travel. But like we discussed, fixed points might not be the answer to every time travel puzzle.
Yeah, that's where underdetermination comes into play. Instead of one set outcome, time travel might lead to a bunch of different outcomes that all make sense in their own way. So it's not just, can this happen anymore? It's more like, how could this happen and still fit with reality?
A much more complex way of looking at it than just assuming time travel would instantly create a paradox. And then there's the question of whether we could ever actually build a time machine.
Which brought us to that partial Kachi surface idea, right? That snapshot of the universe before any time travel shenanigans start. And the question is, Can we see anything in that snapshot that tells us time travel is going to happen later on? Like, are there hidden clues in the present that hint at future time travel? It really makes you think about whether things are predetermined and if the potential for time travel is already there in the universe from the very beginning.
And if it is, does that put limits on what can happen in the normal pre-time travel parts of the universe?
Yeah.
Almost like the universe is adjusting itself to accommodate the possibility of time travel.
Precisely. We might need to think about a whole new set of rules, not just the regular laws of physics, but global rules that come from the very structure of space-time. And then we dove into computational time travel and the easy knowledge paradox.
Where it's not physical stuff that's traveling through time, but information. The idea of a computer with a time loop in its circuits, being able to solve super complex problems in a snap, that's just mind-blowing. It really makes you question the limits of what we can know and what's possible to compute.
Definitely. It challenges us to think about what's possible, not just in terms of physics, but also about knowledge, computation, and maybe even what humans are capable of.
This whole deep dive has been an incredible journey. It really makes you realize that time travel isn't just some fun sci-fi concept. It's something that forces us to tackle some really big questions about reality, cause and effect, and what our place in the universe even is.
Absolutely. And it leaves us with one final thought-provoking question. If we could, hypothetically change the starting conditions of the universe, could we design it in a way that allows for time travel? Or are there some fundamental limits, maybe ones we don't even know about yet, that would prevent time travel from ever happening? That's a question that could keep philosophers and physicists arguing for ages. I think I need a little time to process that one myself. Thanks for taking us on this incredible ride. It's been, well, a real mind bender, but in a good way, of course.
It was my pleasure. Keep questioning, keep exploring, and keep those minds open to all the wonders and mysteries the universe has to offer.